I'm going to show you how to determine the rate law for a reaction when you can't hold a concentration constant in each situation. So this is a little bit different than what we've done previously. It's definitely a lot higher level. It's something you certainly will see in college chemistry. I don't think it's something you'd see on an AP exam, so I don't really stress it anymore. But I think it's really good just thinking practice and making sure that you can really make something work when it's not all the rules that you've learned before. It says, in a hypothetical chemical reaction that has the stoichiometry 2x plus y yields z, the following initial rate data were obtained. All measurements were made at the same temperature. You've run 4 experiments. You've altered the concentrations of X and Y, and you've looked at the initial rate of formation of Z in molar per second. When you look at this data table, the first thing you always want to find is where you can hold the concentration of one of the reactants constant and the other one changes. So where is concentration constant and the other changes? Experiments 2 and 3. You can hold X constant and Y is going to change. Y doubles, the rate doubles, indicating the order with respect to Y is first, because 2 to the M would be 2, and we'll write that out in just a sec. Can you hold Y constant? No. So let's see how to work this. This is the first time you can't hold one constant. We want to figure out the rate law from the data. We're going to work it initially as we did previously. So what we've got here is we're going to hold X constant. We're looking at the effect of Y on the rate in experiments 2 and 3, and that will get you started. You've got 0.40 molar over 0.20 molar, and that is going to be raised to the M power for second reactant, and that's going to be the rate of the second experiment over the rate of the first experiment, and you have 2 to the M is equal to 2, so M is equal to 1. First order with respect to Y. So doubling Y doubles the rate, tripling Y triples the rate, increasing or quadrupling Y quadruples the rate. Whatever you do to the concentration is what you're going to do to the rate when you have first order. Yes? Okay. Now, we want to look at the effect of X on the rate. But we can't hold Y constant in any regard. We need X to change. We need to fix Y constant. And there's a couple different ways that you can go about doing this. I like to look for a simple increase. Keep in mind that X has to change. So which experiments can I absolutely not use? 2 to 3. That's not going to show a change. And remember I said if you divide concentrations and you get 1 to some power, you've made a mistake. So be careful there. It happened one year. It was just a total confusion. We need X to change, and I like to make it simple. I can see here that X from experiments 1 to experiment 3 doubles. I want to set y constant and take the effect out of y increasing on the rate. So there's a couple different ways that I can go about this, and there's no right or wrong, just make it simple for you. If I want to make this constant, instead of 0.4, I want 0.1. So what would I have to divide that by? Okay, well, if I divide this by 4, I have to divide this by 4 to the first power. Oh, my numbers went nuts. Hang on. I'll fix them. There you go. Why 4 to the first power? Because the order with respect to y is 1. So if the order with respect to y was 2, I would divide it by 4 to the second power. So be careful there. That can get tricky. Once I get this value now, I'm essentially holding y constant, and I can look at the effect of x on the rate. So if we take a look at this then, the first thing I need to do is get the corrected rate of formation of z in experiment 3, and that's going to be 2.8 times 10 to the negative third divided by 4 to the first power. That's going to be 0.7 times 10 to the negative third, and this was molar per second. And that is 7.0 times 10 to the negative 4 molar per second. That's my corrected rate 3. And now I'm ready to rock with it. I have x in experiments 1 and 3, so we're going to look at 1 and 3. Now it's 3 star because it's going to be corrected in regard to the rate. So I have 0.40 molar over 0.20 molar to the n, and that's equal to the corrected rate 3 over the first experiment's rate. That's a lowercase s, it's kind of sloppy. So I have 2 to the n is equal to 1. So what's n? Anything to what power is 1? 0. Okay? So our rate law then is going to be, I'll write it over here, I've got rate is equal to k, x to the 0, y, and you wouldn't write something to the 0. So altering the concentration of x has no effect on the rate. And again, not something I think you'd see, and that's why I'm recording separately here, but I think it's very interesting. Also, what I do want to mention here, we don't need to calculate the value of k, but what are the units of k in this instance? In a first order reaction, the units of k are? So it'd be capital M, 1 minus overall order. What's the overall order? 1 minus 1 is?
0.
Anything to the 0 power is? 1. So your units for k are just time to the negative 1, in this case seconds to the negative 1. And we'll get into that in a lot more detail next week. There's another problem here for those of you who really want to try it. It's kind of fun. Really makes you think, and if you can do this, you can do anything.
Why didn't you divide the initial of the x by 4?
The reason why I divided the third experiment's Y concentration by 4 is I wanted the first and the third to be the same. So if I divide, here on the screen, if I divide the third experiment's Y concentration by 4, I essentially set these to be equal to one another. And by doing that, I want to take the effect out of quadrupling Y on this rate. So I divide it by 4 to the first power because we established that this is first order. So if it were second order, I would have divided it by 16. All right? Yes?
Could you have, like, multiplied?
Yes, you absolutely could. And sometimes I do. You could have not done this and not done this, but you could have multiplied here by 4. And then you would have multiplied here by 4 to the first power. So that works too. Same effect. Yep, absolutely works too. Whatever's easier. But again, I don't think they're really going to ask you. But what you absolutely want to be comfortable with is writing rate laws and interpreting them. And what's really kind of interesting is when you link this to calculus. I know a lot of you are in AP calculus. You're learning how to do derivatives and how to integrate. I don't know if you've done integration yet. It's the same concept, and we'll take a look at that next week. I try and link those together and mention it to Mr. Marr, so he does too. Alrighty? What you absolutely positively want to be comfortable with for Monday: writing rate equations, writing rate laws from data, interpreting them. And then you'll be in good shape for what we'll continue with next week.